This presentation introduces the foundational paper, MapReduce, Simplified Data Processing on Large Clusters, authored by Jeffrey Dean and Sanjay Gemawat. When scaling computation across thousands of commodity machines, engineering complexity skyrockets. We will detail the high-level programming abstraction designed to manage massive datasets and automate all low-level parallelization and failure handling. Large technology organizations face critical challenges when processing massive datasets, necessitating computation distribution across thousands of commodity machines. Despite the conceptual simplicity of many required tasks, manual parallelization and robust failure handling introduce significant engineering complexity and extensive boilerplate code. Consequently, there arose a fundamental need for a standardized high-level programming abstraction to manage these low-level details automatically. This presentation details the MapReduce programming model, which leverages map and reduce primitives to satisfy this requirement. The subsequent slides will explain the core programming primitives, the sophisticated execution mechanics, and the fault-tolerance strategies that enable efficient cluster operation. Finally, empirical data regarding the system's performance, scalability, and successful real-world adoption will be examined. This introductory module establishes the critical challenges faced when processing massive datasets, such as crawled web documents and system logs, within large technology organizations. Large-scale data processing necessitates distributing computations across hundreds or thousands of commodity machines to achieve reasonable completion times. Despite the inherent conceptual simplicity of many required tasks, the necessity of manual parallelization, data distribution, and robust failure handling introduces significant engineering complexity. This extensive boilerplate code often obscures the original simple computation, hindering developer productivity and system reliability. Consequently, the need arose for a standardized high-level programming abstraction to automatically manage these messy details. The subsequent slides will detail the MapReduce programming model and how it addresses these requirements by leveraging map and reduce primitives. The MapReduce framework addresses the need for scalable data processing by utilizing a core functional abstraction. The user defines the computation using two fundamental functions, map and reduce. The map function takes an initial input pair and generates a set of intermediate key-value pairs. Critically, the MapReduce library then automatically groups all these intermediate values based upon their common intermediate key. The user-defined reduce function subsequently accepts an intermediate key and the corresponding list of values. It merges these values to form the potentially smaller set of final output results. This structure allows the system to handle value lists that are too large to fit entirely in memory by supplying them via an iterator. After establishing the MapReduce programming model, the implementation details must explicitly address the specific target computing environment. This particular MapReduce implementation targets the large-scale cluster environment currently in wide use at Google. These clusters are characterized by utilizing hundreds or thousands of inexpensive, commodity dual-processor machines. Crucially, the system design must account for the limited networking capacity, specifically the low overall bisection bandwidth provided by switched Ethernet. Due to this massive scale, hardware instability is expected, meaning machine failures occur frequently. Therefore, the MapReduce framework must build reliability on top of unreliable hardware, depending on a robust distributed file system to manage replicated data across local disks. This volatile environment justifies the need for the sophisticated fault tolerance and optimization mechanisms detailed in the upcoming slides. Following the definition of the programming model, the focus shifts to the detailed execution mechanics. The overall flow begins when the user program calls the MapReduce function, initiating the splitting of input files into M distinct input pieces. A designated master process coordinates the assignment of these mmap tasks and the subsequent R-reduce tasks to available worker machines. Map workers read their assigned input split, execute the user-defined map function, and buffer the resulting intermediate key-value pairs. Crucially, these buffered pairs are periodically partitioned into R regions using a specified function, often implemented by taking the hash of the key modulus R. This partitioned intermediate data is written to local disk, and its location is reported to the master for eventual forwarding to the assigned reduce workers. The execution overview diagram systematically illustrates the flow of data and control across the MapReduce job phases. The process begins when the user program forks the necessary worker tasks and initiates the master, which is responsible for coordinating the overall computation. The master assigns map tasks, directing workers to read specific input splits and generate intermediate key value pairs, which are written locally. Once mapping is complete, the master assigns reduce tasks, requiring a second set of workers to remotely read all intermediate data relevant to their assigned partitions. This shuffle phase is critical for grouping identical keys together before the reduce function is applied. Subsequently, the reduce workers execute the user-defined logic, ultimately producing and writing the final integrated output files. This comprehensive flow provides the foundation upon which robust failure handling mechanisms, addressed in the next section, are built. Worker failure handling is crucial for system robustness and relies on mechanisms managed by the master node. The master employs periodic pings to monitor the status of every worker machine. If a response is not received within a set time frame, the worker is marked as failed. Upon detection, all tasks associated with the failed worker are immediately reset back to the initial idle state, making them eligible for rapid rescheduling on healthier machines. Crucially, completed map tasks must be re-executed because their intermediate data is stored locally on the failed machine and becomes inaccessible. Reduced tasks are subsequently notified of the new map worker location, maintaining data integrity, a concept important for the discussion on output semantics. This proactive approach ensures forward progress and makes the MapReduce system highly resilient, even against significant cluster-wide failures. Having addressed how worker failures are handled, the presentation now examines how the system ensures correct output semantics despite task re-execution. If user-supplied map and reduce operators are deterministic, the distributed system guarantees the final output matches a non-faulting sequential execution. This determinism is achieved by having each in-progress task write results to private temporary files. The system relies on atomic commits of these task outputs to uphold the sequential execution property. When a map task completes, the master records the names of the temporary output files. For reduce tasks, completion involves an atomic rename of the temporary file to the final output destination. The underlying file system's atomic rename operation guarantees that the final state contains data produced by only one successful execution, greatly simplifying programmer reasoning. Following the discussion of the overall execution flow, we now examine a critical optimization technique called data locality. The scarcity of network bandwidth within large clusters necessitates minimizing the movement of data across the network. This optimization leverages the underlying file system structure. The Google file system manages input data in 64 megabyte blocks, maintaining multiple replicas of each block across different machines. The MapReduce master actively utilizes this location information during the scheduling phase. It attempts to assign map tasks preferentially to worker machines that already host a replica of the required input data. This strategy ensures that the majority of input data is read directly from local disk, thereby dramatically minimizing network bandwidth consumption across the cluster. Having established data locality optimizations, the system must next determine the optimal number of map, M, and reduce, R, tasks. The architecture mandates that M and R be significantly larger than the count of worker machines. This high granularity is essential for achieving effective dynamic load balancing. Furthermore, increased task granularity accelerates recovery following worker failures by allowing completed tasks to be quickly redistributed. Practical constraints limit task counts, however, as the master node memory scales with a total state proportional to m plus r and m multiplied by r. Map task size is often optimized to between 16 megabytes and 64 megabytes to maximize the locality gains discussed previously. The number of reduced tasks, r, also governs the count of final output files generated. Addressing performance bottlenecks requires mitigating the impact of stragglers, which are machines taking an unusually long time to complete the last few tasks. Stragglers can arise from diverse issues such as faulty hardware, resource contention, or rare software initialization errors leading to dramatic slowdowns. To alleviate this common bottleneck, the MapReduce system employs a general mechanism involving redundant computation. When an operation approaches completion, the master schedules backup executions for the remaining in-progress tasks. The task is subsequently marked complete as soon as either the primary or the backup execution successfully finishes. This strategy significantly reduces the total execution time, often without increasing the overall computational resources used by more than a few percent. Having discussed task execution and failure mitigation, we now examine how intermediate data is assigned to reduced tasks. By default, MapReduce utilizes a standard hashing function to partition intermediate keys across the R desired reduced tasks. This function is typically the hash of the intermediate key modulus R, which promotes well-balanced partitioning. However, simple hashing is sometimes insufficient for requirements demanding strict data coherence. The MapReduce framework therefore allows users to supply a special custom partitioning function. This capability ensures that specific, related groups of keys reliably end up in the exact same reduced task and, consequently, the same output file. By implementing a custom function, like hashing the host name extracted from a key modulus R, related data is guaranteed to co-locate for processing. As map tasks generate intermediate results, situations often arise where there is significant repetition among the generated keys. When the user-specified reduce function is both commutative and associative, this redundancy can be leveraged for optimization. Therefore, the system allows users to specify an optional combiner function designed for performing partial merging of these intermediate results directly on the map machine. This optional step drastically reduces the overall volume of data that needs to be transferred across the network to the reducing task. The combiner typically utilizes the same processing logic as the reduce function itself, though its output is written to an intermediate file rather than the final output destination. Utilizing this partial combining technique significantly speeds up certain classes of MapReduce operations by mitigating network bottlenecks. Figure 2 illustrates the aggregated input data transfer rate across the entire computing cluster during a typical MapReduce job execution. The vertical axis measures input in megabytes divided by second, tracking the system's ability to consume source data in parallel over time. A sharp ramp-up is immediately observed, demonstrating that numerous workers efficiently begin processing their data splits concurrently. The measured throughput reaches an impressive peak of approximately 31,000 megabytes divided by second near the 55-second mark. This high aggregate rate validates the system's design for maximizing parallel input access and network bandwidth, building upon the data locality optimizations previously discussed. Following this maximal parallel phase, the rate drops rapidly back towards zero as the map tasks complete their intermediate data generation. Overall, the processing phase is finished within roughly 80 seconds, affirming the system's capacity for rapid, scalable computation. Figure 3 provides empirical validation of the efficacy of the backup task mechanism by examining the data transfer rates for a large sort operation. The plots illustrate the rates for input, shuffle, and output phases over time across three distinct execution scenarios. Comparing the normal execution shown in Panel A with the execution lacking backup tasks in Panel B reveals a substantial performance penalty. Without straggler mitigation, the overall execution time increases by approximately 40%, confirming the necessity of backup tasks for efficiency. Furthermore, Scenario C demonstrates the robust resilience of the system. Even when 200 map tasks are deliberately killed to simulate widespread failure, the execution finishes in roughly the same amount of time as the normal execution. This visualization confirms that the proposed failure and straggler handling techniques effectively maintain high throughput and reliability in the face of varying operational challenges. The table provides a comprehensive summary of MapReduce production usage during August 2004. During this single month, the system processed 29,423 jobs, consuming over 79,000 machine days and reading 3,288 terabytes of input data. The average job completion time was 634 seconds, achieved while leveraging an average of 157 worker machines per job. Crucially, the statistic showing 1.2 average worker deaths per job validates the engineering focus on fault tolerance and automatic recovery mechanisms discussed earlier. The high degree of parallelism required for these workloads is evident in the average of 3,351 map tasks run per job. Moreover, the existence of nearly 400 unique map implementations confirms the utility of MapReduce across diverse application requirements within the organization. These usage statistics set the stage for evaluating the achieved performance scaling of the system. Attention now shifts from the system design principles to the empirical performance results. This analysis measures the MapReduce framework running two distinct large-scale computations. The first is a grep program, which represents tasks involving data extraction and filtering from a massive dataset. The second is a sort program, which models computations requiring extensive data shuffling and reorganization across the cluster. Both tests operate on approximately 1 terabyte of input data within the established cluster environment. These benchmarks provide crucial evidence regarding the overall throughput and high scalability of the system. Figure 4 illustrates the adoption rate of the MapReduce framework within Google, tracking the cumulative number of separate MapReduce programs committed to the source tree over an 18-month period. During the initial implementation phase, spanning from March 2003 through early 2004, adoption was steady but relatively slow. A clear inflection point is observed around March 2004, indicating a rapid acceleration in the creation of new MapReduce jobs. By September 2004, the number of distinct MapReduce programs had approached 900 instances. This graph depicts a pattern of nearly exponential growth in usage, strongly validating the overall utility and acceptance of the programming model across various internal projects. Such broad adoption confirms the effectiveness of the design choices made for scalability and ease of use, paving the way for deploying MapReduce in crucial large-scale applications, like the indexing system that will be detailed shortly. Having detailed the underlying architecture and performance characteristics, the focus shifts to the system's most significant application: the complete rewrite of the production web indexing service. This new pipeline processes the raw contents of documents, which constitutes more than 20 terabytes of input data. Utilizing the MapReduce framework significantly reduced code complexity because the intricate logic for fault tolerance, distribution, and parallelization is inherently managed by the underlying library. For instance, the size of one critical computational phase was reduced from approximately 3,800 lines of C++ code to only 700 lines. This improved architectural simplicity also translated into enhanced flexibility, allowing complex modifications to the indexing process to be completed in days rather than taking several months. Furthermore, operational oversight became much easier because the MapReduce library automatically handles failures and performance degradation without requiring manual operator intervention. Before concluding the presentation, it is essential to position MapReduce within the landscape of existing distributed systems. Many systems, such as parallel prefix computation and bulk synchronous programming, utilize restricted models to facilitate automatic parallelization. However, MapReduce is fundamentally distinguished by its robust, built-in, and transparent fault tolerance. While systems like Message Passing Interface, or MPI, often leave failure handling to the programmer, MapReduce scales reliability across thousands of commodity processors. This scaling ability is due to its deliberate distillation of prior models, coupled with specialized mechanisms such as the use of backup tasks. Furthermore, its crucial data locality optimization is conceptually similar to active disk techniques, pushing computation closer to the data storage. The success of the MapReduce programming model can be attributed to three primary factors: usability, broad applicability, and robust implementation. First, MapReduce is easy to use for non-distributed programmers because it abstracts away complexity like parallelization and fault tolerance. Second, the programming model applies effectively to a wide variety of large-scale computing tasks, including sorting and data mining. Third, the developed implementation scales highly efficiently to clusters comprising thousands of machines. Overall, the study demonstrates that constraining the programming paradigm significantly simplifies distributed computation, enabling powerful optimizations such as data locality and redundant execution for handling slow machines. These core characteristics ensured MapReduce's successful deployment across numerous large computational problems.